Okay. Tried to simplify this setup as much as possible. It's still just something weird with this cable in the projector. Okay, so what did you guys think of did you do the lab yet? What'd you think? The question's super hard. Okay. Okay. I don't want to be super, I mean, that's why it's like, it's extra credit if you do the questions even. Yeah, I just want to try something because we didn't have the quiz and there wasn't a lab, so. Grape soda, making grape soda from gloves. Okay, so for today though, talking about heat of vaporization. We did, wait a second, these are the wrong slides. Those are my slides from the other class. It's Chem 20. Oh yeah, we're already on solutions. Okay. Ionic concentrations then, right? So we talked about how to use molarity as a unit conversion. And we can convert between moles of something and liters of something, as long as we know the molarity. Molarity being in units of moles per liter. We can also get to grams, because if we can get to moles, then we can calculate how many grams that is. So we had 1 molar glucose solution, indicates that the solution contains 1 mole of glucose, which is the C6H12O6, per 1 liter of solution. When ions dissolve into solution, so these are like ionic compounds, it's a little bit different. These ions break up into the constituent cation and anion. So here, for example, we have sodium chloride. Oops. And when we drop that into a solution as the solid table salt, it'll break up into our sodium ions plus our chloride ions. So in this solution now, when we have 1 molar sodium chloride, indicates that we have 1 mole of sodium and also 1 mole of chlorine, because you need that many of each to make a single molecule. We can also use this idea as a conversion factor. So it doesn't have to be 1-to-1. For example, in sodium phosphate, we have sodium, or in our sodium phosphate, I should say, we have 3 sodium atoms and we have a single phosphate. So that's one of our polyatomic ions. And we treat those as sort of a single unit. So if we have 1.5 molar sodium phosphate, and we want to find the amount of sodium, say that we have 3 sodium atoms per every 1 sodium phosphate. So we can use this as our conversion factor. And say that for every, so 3 sodiums, for every 1 sodium phosphate. So we're actually going to have 3 times as much the molarity. So it'll be 4.5 sodium ion concentration. And you'll know that this is going to happen because this is an ionic compound. Specifically that we have just as a refresher, I should say, it's a metal plus a non-metal. And that non-metal can be a polyatomic ion, or it could be a single non-metal atom. Solutions are normally concentrated to save space. And so, I mean, it's concentrated because if we have something like a 1.0 molar, should say sodium chloride solution, that's 1 mole of sodium chloride per 1 liter of solution. We can change the volume of the solution without changing the number of moles that are in that solution. So for a sodium chloride solution dissolved in water, for example, you might take that and you might boil it down because the rest of this solution is just water. It's not really important. We can add water, we can remove water, at least in the case of sodium chloride, fairly easily. But to determine, it's much harder to make something more concentrated than it is to make it more dilute. So we use this equation for dilution. And you'll notice that it takes a similar form to our gas law equation of P1V1 equals P2V2. Here we have M1V1, so molarity is M, equals M2V2. And we use these in a similar way to that we use the ideal gas law equations, where we have some set of initial conditions, and then we're looking for a new set of conditions. So let's use this example here. We have a stock solution of 2 molar sodium chloride, and we make 1 liter. Wait, let us take stock solution, oh yeah, and make 1 liter of 1 molar solution. So be sure to prepare it properly. I think what that's hinting at is the fact that, well, let's do the calculation and then I'll explain what this be sure to prepare it properly means. Okay, so here we have a stock solution. So this is going to be our M1. And we want to make 1 liter. This is going to be our V2 of 1 molar solution. So 1 molar solution. That'll be our M2. So we can plug these into this equation. 2 molar sodium chloride times V1 equals 1.0 molar sodium chloride solution times our V2, which is 1.00 liters. So really the question that's sort of hidden inside of this question is, how much of our 2 molar solution do we need to add to make this 1 liter of 1 molar solution? So we can just use a little algebra. I don't have much space here, so I'm not going to show too many steps. On this side, it's going to be 1, and then we're going to have 2 V1, and then we can do divide by 2 on both sides. And I'm going to move to the right here. So V1 equals 1/2 or 0.5 liters. And that V1 is 0.5 liters of the 2 molar sodium chloride. I should have slide previews on here so I can see the next one. Let me see. Okay. Just be sure to make it properly. What that means is if we took a beaker, let's just zoom in. So if we had a beaker and we filled this up with exactly 1 liter, right? Because, oh, we want to end with a 1 liter solution. Well, if we take then our smaller beaker over here of our 0.5 liters, and we dump this into the 1 liter, now we have 1.5 liters. So you're always going to start by adding in your smaller amount and then diluting up to your final volume. Same thing if we had a solid. So if we wanted to make a solution, for example, if we wanted, again, to make a 1 molar 1 molar, 1 liter solution, but we're going to use solid salt, we wouldn't add 1 liter of water first and then add in the solid sodium chloride, because by adding that solid, we would increase the volume and then our molarity would be less than what we actually wanted. So to what volume, there's a hint there, should you dilute 0.100 liters of a 15 molar sodium hydroxide solution to obtain a 1 molar sodium hydroxide solution? So again, we can set this up same way. We're gonna have a V1, M1, V2, M2. So our V1 is 0.100 liters. M1 is going to be 15 molar sodium hydroxide. And then our V2 is what we're solving for. So unlike in the last question, we're given explicitly what that variable is, rather than having to infer it from the format of the question. But we want our final molarity to be 1.0 molar sodium hydroxide. So M1, V1 is M2, V2. And then it's just another plug and chug operation. And this times 0.100 liters equals our M1, which is 1.0 molar, times V2. So I'll give you a little more time to write. Let's finish this. So if we're going to do, I have space here, so I'm going to show the units more clearly than I did in the last one. When we multiply 15 molar by 0.1, we're going to move the decimal place 1 to the left. You do it on your calculator too. We'll get 1.5. And then our units here, won't say add, but they multiply together. So we've got moles, liters there. On the right side, we're going to have 1.0 molar and our V2. So then when we divide both sides by this 1.0 molar, these units of molarity will cancel out and they will give us our desired units. So we get 1.5 liters equals V2. So unlike our ideal gas law or gas law equations in general, did I do my math right? 1.0. Just make sure, because this is our V2 or M2, I mean. So we want to, because we have V2 on the right side, so we're going to remove the 1.00 over. So unlike our gas law problems, the only units that you need to worry about here is that they're the same units. Or I should say, molarities. We might talk about another unit called molality, which is confusing for no reason. But molarity is the concentration unit that we're going to be using most commonly. I know, nope, that was Chem 20. So things just need to be in the same units on either side. Concentration does need to be in molarity, but we don't use another. Actually, I shouldn't say that we don't use another concentration unit because we might. So molarity, and then it can be in liters or other units for volume. Oh, perfect. The units just have to match. So now we want to know the molarity of a solution in which 100 milliliters of 1 molar potassium chloride is diluted to 1 liter. So again, we're going to have M1 or V1 M1, V2 M2, and our V1. So what is the molarity of a solution in which 100 milliliters, keep that, of 1 molar potassium chloride is diluted to 1.0 liters. And then molarity, again, is a question that we're trying to answer, or the variable that we're solving for. So here we have different units. We have milliliters and liters. So we need to convert one of those into, we need to convert one of those into the other. So we could convert liters into milliliters, or we can convert milliliters into liters. I'm going to convert milliliters to liters. So this is going to divide by 1,000. Or move the decimal place over to the left three spaces. And we'll get 1.000, oops, sorry, 0.1000 liters. And then we'll just set up M1, V1, M2, V2. So we'll have 1.0 molar potassium chloride. And we'll have our volume now calculated in liters, 0.1000 liters. Molarity is what we're looking for now. And then our V2 is going to be 1.0 liters. So a lot of ones in this problem. So when we multiply this, we're going to get 0.1000 molarity liters equals our M2 times 1.0 liters. And since we want to isolate that M2, we're going to divide by 1.0 liters. And again, our units can cancel there. This whole thing will cancel there. I'll get 0.1000 molarity as M2. And if we want to do the correct number of sig figs, be 0.10 molar. Be careful. My M's can start to look like mu's. Oh wow, there's only 3 slides left. So we're gonna get into the next chapter then. So in a similar way that we can use gases and the gas laws to plug numbers into a stoichiometry problem, we can also use solutions and now the solution equations that we know to plug values into stoichiometry problems. When chemical reactions involve aqueous solutions, we use the balanced chemical equation, the molarity, and the volume to determine the moles or grams of a reactant or product. For example, we can determine the volume of solution from the molarity and the grams of reactant as seen in this problem. So we got zinc reacts with HCl to produce hydrogen gas, which they very kindly give you as H2, and zinc chloride. How many liters of a 1.5 molar HCl solution completely react with 5.32 grams of zinc? So for any stoichiometry problem, we need to be working in terms of moles. So we're going to convert each of these into moles. So for zinc, let's see here. Zinc is 65.39. See, the wording of this question is tricky. So actually, let me ask this. What do you think we're solving for here? Yeah. How are we going to get there? Conversions. Okay. So here, help me make a, let's make a solution diagram actually before we get started converting these things. In my mind, if I ever get to a problem where it's not entirely clear the route that I need to take, I'm just going to start converting things into moles. Right, so in this case, because we're looking for liters, we're going to be using molarity, as we talked about earlier, can be used as a conversion factor. All right, so we're going to be able to convert from moles to liters there. So then that leaves zinc as our only thing that's not a conversion factor. And that's going to be our given. So we're going to start with grams of zinc. And what's going to be our next step? Moles of zinc. After we've got moles of zinc, what's our next step? Moles of HCl. And then moles of HCl, using our molarity, you can actually calculate liters of HCl. Excellent. All right, so we can calculate our, well, let's set it up like the stoichiometry problem that it is. So we're going to have our grams of zinc of 5.32 grams zinc, 65.39 grams of zinc for every 1 mole zinc. And then so grams, now we have moles of zinc. So now we want to calculate moles of HCl. And so we'll use our ratio from our reaction equation here. So for every 1 mole of zinc, we're going to need 2 moles of HCl. Oh, actually, this, yeah, that is it. Okay. So 1 mole zinc, we're going to need 2 moles HCl. So we've calculated then our moles of HCl. Now we want liters of HCl. We're going to use our 1.5. And again, molarity is in moles per liter. And so I'll have 1.5 moles HCl for every 1 liter HCl. I actually remember very distinctly having to write out molarity, the units for molarity over and over and over again to finally remember what it is. And then this number that you're given for molarity is always going to be the number of moles per the liter. All right. So if we have 5.32 times 2, I'm just multiplying across the top. And then I'll divide by everything that's on the bottom. So divide by 65.39, divide by 1.5. And we're going to need 0.108 liters of HCl. This is a good one. This reaction equation is a good one too, because we also end up with a gas. All right, so we could calculate the number of moles of the gas that are created. And then if we had, volume and temperature, we could calculate the pressure, or if we had pressure and temperature, we calculate volume. All right, so there's all these things that we can calculate with really just a handful of simple equations. All right, so how many milliliters? I don't think I'm going to give you any questions that are going to be like trying to like sneak in a separate unit to like get you to, I don't know. This is the kind of question that seems sneaky to me. It's like, why are we working in milliliters? Why can't it be liters? Or I'll underline it if I do. Because the point would be to see if you can convert it, not to see if you're paying attention under a stressful test situation. I don't know. Okay. So similar problem to the last one. We want to know how many milliliters of this 0.25 molar barium chloride solution are needed to react with a volume now of a different molarity sodium sulfate solution. So again, we can look at these and we can say, okay, well, what are our conversion factors? What are we looking for? We're going to end with milliliters BaCl2. And we're going to start with, because molarity can be a conversion factor, it can also be the thing that you're trying to solve for. But in this case, we're given a volume of this solution. So that's what we're going to start with. So we're going to be starting with the 0.03, actually, I'll do it this way. Again, solution diagrams are super helpful because a lot of your thought process can go into laying the path before you, and then you're not trying to remember what you were trying to do as you try to find the right conversion factors when calculating problems. So we're going to liters, Na2SO4. From there, we're going to convert to moles. Because again, for every one of these stoichiometry problems, almost always, if not always, actually, take that back. You always need to go to moles if you're going to convert from one element or molecule to another one using a reaction equation. So moles of sodium sulfate to moles barium chloride. Once we have the moles of barium chloride, hey, there we go. We can calculate the milliliters of barium chloride. So again, we can set this up like a stoichiometry problem. 0.0325 liters, Na2SO4. And then just also, this is molarity is going to be in moles per liter. So to convert from liters of sodium sulfate, we need to use our molarity to calculate the number of moles. 0.160, oops, sorry, did that upside down. 0.160 moles Na2SO4. And that's going to be per 1 liter of this Na2SO4 solution. And then that gives us moles of sodium sulfate. And now we need to get to moles of barium chloride. So we can use our reaction equation. Easy enough, it's 1 to 1. So for every 1 mole barium chloride, we'd be reacting with 1 mole of sodium sulfate. Wait, I did that upside down. The right number's in the wrong order. If we did it that other way, then we don't end up with units, the units that we want. Okay. We have moles of barium chloride. And then we want to go from moles of barium chloride to milliliters of barium chloride. I guess I should have done this. Because there's going to be another step here. Because we're going to do liters of barium chloride first, because molarity is in units of moles per liter. So we have 0.25 moles BaCl2. That's going to be 1 liter BaCl2. And then to get from liters to milliliters, we just multiply by 1,000. Wait, yeah. There's 1,000 milliliters in 1 liter. So we multiply across the top, 0.0325 times 0.16 times 1,000 divided by 0.25, because it's the only number that we have on the denominators that's not 0. So we're going to get 20.8 milliliters of barium chloride solution. Good. And the last one's the homework. Is there anybody on? Oh, there's a bunch of people on Zoom. Nice. We'd love to see it. Okay, well now I need to download the next slides because I haven't done that yet. So you guys get to look at how disorganized my OneDrive is. Chapter 13. Let's see if this looks okay. Sometimes the PowerPoint files look really, really bad. Okay. Let's make sure there's no pictures covering up text, so that there's not too much text running off the screen. Okay. This is another short one. Ooh, fun. Reaction rates and chemical equilibrium. Yeah, if you didn't know already, basically everything exists in equilibrium, and not a static equilibrium, but a dynamic equilibrium. So the amount of water that exists in the Central Valley is a function of how much water, well, how much water we really ends up going out through rivers into the ocean, or ends up being bottled and taken to other states. And it's also a function, though, of the amount of rain that we get, which is why every time it rains, we're hoping that the drought will end, but it doesn't necessarily. And that's the water cycle, right? So if we've got the Central Valley, we got water that goes up evaporation, it goes up into the clouds, it goes to the mountains. Usually it doesn't rain so much around here. It rains in the mountains, and then it runs back down to the valley. So it's this dynamic equilibrium. So if the amount of water coming in slows down, then we have less water here. Another huge dynamic equilibrium, and one that's, whether you believe in global warming or not, one that's really slowed down the rate of, or the amount of CO2 that's in the atmosphere, is the ocean. So the ocean, with all this little fish, actually acts as a huge sink for CO2. So we pump CO2 out from our cars, from electricity generation plants. Also, wildfires release a ton of CO2. A lot of that CO2 gets absorbed by the ocean. And then at the very bottom of the ocean, that CO2, oh shoot, is it sodium carbonate? I think it's calcium carbonate, which is lime. So eventually, that CO2 becomes carbonate, and then it'll eventually settle and drop out of the ocean into lime at the bottom of the ocean. So there's this dynamic process, but this arrow down here, this rate that it's turning into lime is really small compared to the amount of CO2 that's going into the ocean. And for the ocean, what that means is you get a lot of H2CO3, carbonic acid, which is why we have ocean acidification, and it's killing coral reefs and stuff. In theory, if we can slow down this rate, we slow down the rate that we're dumping CO2 into the ocean, then eventually this really small force maybe won't speed up, but it can catch up to the amount of CO2 that's been put into the ocean. So these things all exist as dynamic equilibrium. Chemical reactions are no different. And chemical reactions are rate dependent. So there are some slow reactions, there are some fast reactions, right? Rust is a relatively slow reaction. But burning is a very fast reaction. Explosions even faster. So we can calculate the mass of products formed, but time is also a factor. So a reaction doesn't go, it's not a binary where it's, let's do it like this, where it's unreacted and then suddenly it's all reacted. It'll be a curve where the amount of products will slowly increase over time until it finally maxes out. And the rate of this reaction depends on how the reactants interact. So this is also why solids don't react. You mix two solids together, the atoms don't really come into contact with each other, so they don't react. But you put them into a solution, and now they're moving freely around each other. They're able to react much more quickly. Right, and so this is why the reactants must collide with sufficient energy and also the correct orientation to make a product. Then the product is a combination of the reacting material. But not all collisions result in product, right? Because if they don't interact or collide with sufficient energy at the correct orientation, nothing happens. And in at least reactions like this, where we have two things coming together to form a new product, well, these ones are not reacting, to form a new product, the bonds between the nitrogen and the oxygen here, resume. The bonds between the nitrogen and the oxygen have to be broken in order for these new bonds to be formed. So that energy that's required to react is the activation energy. That's the minimum amount of energy needed to cause reaction. So if we don't have that, minimum amount of energy, then we can't, we can't make and break bonds. So we have to break the bonds of the original atoms first, and then have enough energy from that to make the new bonds of our product. So from this figure, the reactants absorb energy. So they're absorbing energy to the point where those bonds break, right here. And then they form a new product that actually has lower energy than the activation energy. And this is how we diagram them. So this is the progress of the reaction, whether it's a reactant or a product, and the energy increase. So we have to get up to this point to get over the hill. If you don't get over the hill, then you just roll back down. The rate or speed of a reaction is determined by measuring the amount of reactant used up or the amount of product formed in a certain time period. So we get a change in the concentration of reactant or product. So usually represented as a delta, which we've seen in Q equals MC, big C, delta T. So delta T means change in time. So here we have delta, so we have a change in reactants or products. And then we also have a delta T, or change in time. So if we use this idea of rate of reaction with this analogy of eating a pizza, when we start to eat, we have a whole pizza, but as time goes by, there are fewer slices of pizza left. And if we know how long it took to eat the pizza, we could determine the rate at which the pizza was consumed. So if we assume 4 slices are eaten every 8 minutes, that gives us a rate of half a slice per minute. After 16 minutes, the entire pizza will be gone. So there are really just a few things that affect the rate of a reaction. The biggest one is temperature. So if you remember that we have this curve where we have to have enough activation energy, should be level there. We have to have enough activation energy to make this reaction happen. One of the ways we could do that is by increasing temperature, because temperature, if you remember from kinetic molecular theory, is the average kinetic energy of the molecules. So by increasing temperature, we increase the available energy for reactions to happen, and then more reactions can happen, and our rate increases. And then as a rule of thumb, a 10 degree rise in temperature will usually double the reaction rate. Rule of thumb. So if you increase the temperature of your body, it causes your metabolism to rise and your heart rate goes up and you breathe faster. And we can put food in the fridge or freezer to slow reaction rates or food spoilage. The other thing that affects a reaction is the concentration of the reactants. This should say reactants, I believe. The interesting thing about if the concentration of the reactants affects our rate, then that means that as the reaction proceeds, it slows down because we have fewer and fewer reactants to react, and that's fewer and fewer possible reactions that can happen. So if you're really, really interested in this, you can go look up some statistical mechanics because all of this is based on how likely the atoms are to react and how many reactions there are going to be. So if we can increase the oxygen in your bloodstream, it allows more oxygen to be delivered to your cells. You can breathe more easily or run faster longer. It's a VO2 max is the measure of how efficiently your body can use oxygen. Another note on, right, so we need this, where does it say? Increased kinetic energy. Well, we need this, right? The activation energy is super important. So do you guys know what heavy water is? Deuterium. So you've talked about isotopes. You know what isotopes are. So hydrogen, right, is a single proton. But we can have deuterium, which is hydrogen. This would be, oh, I put it on the wrong side. One proton, one atomic, oh, sorry, yeah, one proton, no neutrons, that's the atomic mass. Deuterium has, oh, now I'm forgetting how to write these. All right, well, hydrogen has one proton, no neutrons. Deuterium has one proton and one neutron. So it's twice as heavy as hydrogen. And if you actually drink, so if you drink too much heavy water, these deuteriums will start to replace hydrogens in your body. And at a certain point, you'll have so much deuterium, these are heavier, So it's harder to get them to move in reactions. The reactions in your body will slow to a point where you can no longer sustain life. It takes a lot of deuterium, and it's really, really hard to get that much deuterium. But that's all based on reaction rates. You'd need to be warmer to be able to sustain the reactions. Oh, this is problematic terminology. So catalysts, they don't speed up. No, they do speed up the reaction rate. Catalysts can speed up the reaction rate by lowering the activation energy. So this would be kind of like, yeah, this is a good example. Let's say we have this river. All right, so we got this river. And our reaction is people trying to cross the river. So currently, people have to hop in and they have to swim across the river to get to the other side. That takes a lot of energy. There's not a lot of people who are going to be willing to just swim across the river. Our catalyst would be like building a bridge across this river. So now instead of having to swim across, it's very, very easy to just walk across the bridge to get to the other side of the river. So by decreasing this activation energy, we now have more atoms that are able to hit that activation energy to react and finally go to the final product. Okay, so let's look at this example here, 13.6. And how would each of the following change the rate of reaction shown here? We haven't actually talked about this principle exactly. Well, yeah, we did. So if we add some more nitric oxide, is that going to increase the rate of reaction or decrease the rate of reaction? It'll increase the rate of reaction because we're adding more reactants. If we decrease temperature, we'll decrease the rate of reaction. If we remove some hydrogen, we're decreasing the number of reactants or the concentration, so we're going to decrease the rate of reaction. We add a catalyst that we just talked about. We're creating an easier route for those molecules to react. We'll increase the rate of reaction. I guess we haven't talked about equilibrium points yet. So then our three things are increasing temperature, increasing reactant concentration, or adding a catalyst. All speed up our reactions. And they do so by changing how we know that things react. So increasing collisions, decreasing activation energy, and also increasing available energy. So if you can modify a reaction in some way to change any of those three in those directions, then you'll speed up the rate of reaction. So usually, I say usually, up until this point, we've only talked about reactions happening in the forward direction. We say it all goes, all reactants to all products, and now we've learned that, well, maybe that'll take some time. But the truth is, like I mentioned with, the water cycle and CO2 in the ocean, it's a dynamic equilibrium. So we've considered this forward reaction, but for a lot of reactions, there's a reversible reaction. So two of our atoms can collide and sort of undo the reaction that they had just done. So we have two reaction rates then. We have one reaction rate that's forming products, and we have another reaction rate that's reforming our reactants. I want to grab this. So this is just from the previous slide. It's 2H2. Make sure I got that all right. 2H2O. So instead of having this be a reaction arrow just in a single direction, we can change that to more accurately represent that there's a reaction that goes in a forward direction and a reaction that happens in a reverse direction. So these are going to be interacting and hitting each other and forming products. But every once in a while, our products will run into each other and form reactants again. And so there's a balancing act then between this forward reaction and the reverse. That was the other thing I wanted to say about this. So then at the beginning of a reaction, and that's what this graph is, well, kind of what this graph is. The beginning of this reaction, when we add our nitric oxide and our hydrogen, those are the only things in the flask. So they have the highest concentration. But as this reaction, so we've got black line is going to be reactants. So as this proceeds, this is going to slowly lose, sorry, it's probably going to go like this, slowly use up all of our reactants. And then as we make more products, that concentration will increase. And as that concentration increases, we talked about the rate also increases. So the rate will decrease as we lose our reactants, and for our products, the reverse reaction will start to increase until they reach a point where they are the same. And then we'll have sort of a static, well, not a static, we'll have a dynamic equilibrium. Yeah. Oh, good, that was the next slide. Right, so eventually these rates will balance out, and then that's where we end up with these concentrations. So there are certain situations where you can go to a full complete reaction, and that usually involves removing one of your products. Because if you remove that product from the solution, then it can't react to form your reactants again. Most reactions, and the reactions for, well, you guys haven't done that much lab work in this class, but if you take Chem 20 or more chemistry, they're designed to be reactions that go almost to completion. Because we end up at this level where we still have reactants here, there's still an amount of reactants there. Even though we have a lot more of our products, we can't use up all the reactants because our products keep breaking apart and going back to our reactants. So this is just an example of this sort of visualize, right? So here, on this first one, we've got hydrogen and iodine. We have only hydrogen and iodine molecules. So our forward reaction is happening very quickly. But as we progress forward in time, now we have some products, and there's a chance that those will undergo the reverse reaction and become reactants again. As we react more and more of our products, react more and more of our reactants, our number of products increases, and so does the rate of that reverse reaction. Until we finally get to this point where it looks like at about 6, we've maintained some sort of equilibrium. So before equilibrium is reached, the concentration of the reactants, I'm done here. The concentration of the reactants and products, is it equal, not equal? I guess this would be equal or not equal, not faster or slower. There's no room for me to write. So that would be not equal. And then initially, reactants placed in a container have a blank rate of reaction, then the reaction of the products. So since we have only reactants, there's no products, there can't be a rate for products, it's going to be 0. So I'm just going to put a greater. So we'd have a greater than or faster. No, it says faster. What a weird question. And then at equilibrium, the rate of the forward reaction, is equal to the rate of the reverse reaction. Equilibrium. So those rates are equal. Oh boy, you guys even get into equilibrium constants. We'll go back to this though. So one of the things, I guess we didn't really talk about that, did we? One of the questions that I might ask on a problem like this. So if we've got our hydrogen, I just want this to be bigger. We have our iodine. We have a reversible reaction arrow. We have 2 hydriodic acid. So if we have this, and I say, okay, this is at equilibrium, I might ask, which way will the reaction shift if I add more hydrogen? So if we add more hydrogen, then we've increased the amount of our reactants relative to our products. I should use an up arrow. So we're going to shift this reaction to the right because we'll end up forming more products until we form or reach another equilibrium. Or I might ask, what happens if I remove hydrogen? So if we decrease the amount of hydrogen, which way is this reaction going to shift? In that case, it would shift to the left because we are taking some of those away. So we're going to have more products than we had at equilibrium. And so they will form more reactants to balance that out. Surprised I didn't explicitly say this, but it's, I don't want to spell it. Le Chatelier's principle. Le Chatelier, maybe? He's French, so who knows how it's spelled. So many consonant sounds that get dropped. So we have these equilibrium expressions as a way to quantify this idea. At equilibrium, the concentrations of each of the products and reactants can be used to set up a relationship between the products and reactants. So suppose we write this general equation for reactants, A and B, which form products, C and D. Our equilibrium expression, I should zoom in on this. An equilibrium expression we use, just in case it's not super clear, Kc, for a reversible chemical reaction, multiplies the concentration of the products together and divides by the concentration of the reactants. So this is one of those things that's going to be like it's like one of the mantras of chemistry. Products over reactants. So for any of these equilibrium expressions, you're always going to have the products divided by reactants. And then we take each concentration is raised to a power equal to its coefficient in the balanced chemical equation. So here we have, it's like decently clear. I'm going to rewrite it though. All right, so we have, brackets also indicate concentration. So the concentration of C raised to the power of its coefficient of C, concentration of D raised to the power of D, and then concentration of A to the A, and concentration of B raised to the B. This equals Kc. So this tells us about the relative proportion of concentrations between our reactants and our products. So let's a little more practice. So write the equilibrium expression for our hydroiodic acid. So Kc equal to, and again, we're going to have products over reactants. So since we don't have numbers to put in here, we'll just do the concentration of Hi raised to the second power because its coefficient is 2. And then for our denominator or our reactants, H2 and I2. Since their coefficients are 1, we raise them to the power of 1, but anything to the first power is itself. Oh, there has been a chat. Oh, yes, there are non-reversible reactions. Usually a non-reversible reaction is, like I was saying a little bit ago, I don't know how long ago your question was. If we have a reaction that is two liquids, for example, if we had HCl plus Na2CO3, and this reacts to form hold on, that's getting a little more complicated. This is simpler. If you're burning something, so let's say it's methane plus oxygen gives you CO2 plus H2O. This is a non-reversible reaction, or not spontaneously reversible. The CH4 is all going to burn with the oxygen, and none of that is going to recombine back into CH4. The other example might be if you have two liquids that are reacting together to form a gas and another liquid component. In that case, the gas leaves the solution and so can't participate in a reverse reaction. Okay. Sorry, I got a little distracted. I wanted to say, go ahead and try to do this on your own. And then I'll go through it and then we can see how those compare. So we're gonna have products over reactants again and raised to the power of their coefficient. So that's our product. Our reactant is SO2 to the second, O2 to the first. Again, because it's to the first, it's implied. We don't need to write it. I'm like almost going to get through 2 chapters today. Cool. So hopefully what I wrote matches up with what you wrote. If it doesn't, hopefully there's questions. But otherwise we can move on. So knowing these concentrations, and so, right, you can see why the previous chapter was important because we talked about solutions and molarity, which is a concentration. You need molarity to do these kinds of problems. So our equilibrium constants are a ratio between the amount of products and the amount of reactants that we have. So in this equation, for example, there are these 3 different experiments which start with different concentrations of either products. Oh, these are the concentrations at equilibrium. Oh, I see what you're saying. Okay. So at equilibrium, right, these are all different concentrations for the individual things. But when we plug them into this equilibrium equation, we end up with the same number. So the equilibrium constant is always 54 for this reaction at this temperature. And that means that we have 54 products, or 54, basically 54 products for every one reactant, or 1 unit of reactants. So this reaction favors the products. Higher ratio means that we're going to form more products than we are going to form reactants. Let's do this 13.4. I have to go for a thinner pen. So this decomposition of dinitrogen tetroxide or tetroxide forms nitrogen dioxide. So what is the numerical value of Kc? So it's our equilibrium constant. At 100 degrees C, if a reaction mixture at equilibrium contains 0.54 molar dinitrogen tetroxide and 0.31 molar nitrogen dioxide. So first step would be to set up our equilibrium equation. We're going to have products over reactants. So this will be the concentration of NO2 raised to the second power divided by the concentration of N2O4, again raised to the first power. So we can plug these numbers in that we've been given. We'll get 0.31 molar squared over 0.45 molar. So this is going to be 0.21. So our Kc will equal 0.21. Now, does this reaction favor products or reactants? The reactants. Yeah, because our number is less than 1. So really, if it's greater than 1, then we're going to have more products than reactants. If it's less than 1, we're going to have more reactants than products. When reaction mixtures are heterogeneous, the concentrations of solids and liquids remain the same. We do not count them in the reaction equilibrium expression. Yes. So this is when it becomes important to write down the state of the different constituents. So in this case, H2O is a liquid, and so we leave it out of our equilibrium expression. So let me highlight this. So solids and liquids get left out of equilibrium expression. So if Kc is going to be equal to our products over our reactants. Again, this is a liquid, so we leave it out. So Cl2 squared or HCl to the fourth. This is multiplying times O2 raised to the first. Part of the reason that we leave out something like, well, for this reaction, these are in the gas state. So this is kind of similar to what I was talking about, where something might leave the solution, or leave, in this case, becomes a liquid in this gas reaction. Now, in this case, you probably will be able to have the gas over the liquid react with some of the liquid again. But it still gets left out of the equation, especially if we do something under aqueous conditions and we have water, then we have a tiny amount of our products and reactants that's not water, and then by comparison, an infinite amount of water. So it breaks the equilibrium expressions. Oh, that was the question. I thought we had to plug numbers in. Right, so that would be that. Just leave liquids and solids out. Let's see if there's a question about that. Nope, okay. So we can use these equilibrium constants, like I mentioned, to determine whether or not we're going to be product or reactant favored. So the values of Kc can be large or small. They can be really large or they can be really small. And the size of the equilibrium constant depends on whether, right, we're favoring more products than reactants or more reactants than products. Yeah, but the size of the equilibrium constant does not affect how fast equilibrium is reached. It just says that's where we're going to end up. It says nothing about how long it's going to take to get there. So if we have an equilibrium with a large Kc, then we're going to be converting a lot of our reactants into the product. So here we have, some reaction equation, but our I guess it doesn't give numbers to put in here, but because this Kc is 3.4 times 10 to the 2, then we have mostly products and just a few reactants. We have an equilibrium with a small Kc. When we reach an equilibrium constant, the mixture contains a high concentration of reactants and a low concentration of products. Right, and that makes sense because we're dividing, if you take a small number divided by a large number, you're going to get a really small number. All right, so we can calculate then equilibrium concentrations using Kc. So at equilibrium, a reaction with a large Kc contains mostly products, whereas a reaction with a small Kc contains mostly reactants. So here we have a Kc of 1.2. So that's slightly larger. It's larger than 1. So we're going to have a moderately more products than we would reactants. All right, so for the reaction of carbon dioxide, and hydrogen, the equilibrium concentrations are 0.25 molar CO2. Okay, good. I thought this was a different kind of problem. So we have these three concentrations. So one of the keys for these is that it says the equilibrium concentrations. All right, so we're at equilibrium, and we know that we have a concentration of CO2, a concentration of hydrogen, and a concentration of water, and we're also given Kc. So we can write our Kc or reaction or equilibrium constant equation and note that all of these are gases. So we're going to get the concentration of H2O times the concentration of carbon monoxide over the concentration of CO2 and the concentration of hydrogen. We're asked to find the equilibrium concentration of carbon monoxide. And that's not too hard, because we can say that, actually maybe I should write this. So our Kc is going to be 0.11 equal to, and I'm just going to take these and I'm going to fill in all of the numbers that we have. So one of the easiest ways to slip on this, let's put the wrong numbers in the wrong spot. So 0.25 molar, it's our CO2. Hydrogen is going to be 0.8 molar. Oh, all right, we'll finish this quick. Carbon monoxide is what we're looking for. So we can leave that as CO. Oh, let me move that over so it matches. And then water here, note that we're including water this time because it's gaseous water. It was liquid water before. And that's going to be 0.5 molar. So now we just need to solve for carbon monoxide. And as always with algebra, there's multiple ways you could do this. I'm going to do 0.25 times 0.8. Now I'm going to do 0.5 divided by that answer. Oops. It's 0.2. Now I'm at 0.11 equals 2.5 molar times carbon monoxide. So if we do 0.11 divided by 2.5, we'll get 0.044 molar as our concentration of carbon monoxide. All right. Let me end the recording.